mathematical modeling. Today, I will going to explain about Chapter 8 Mathematical Modeling. What is mathematical modeling and why we must study this chapter? A mathematical model is a representation of a system or scenario that is used to gain quantitative and/or quantitative understanding of some real-world problem and to predict future behavior. Why study this chapter? Mathematical modeling is used in various disciplines in the real world. Engineers use mathematical modeling to analyze the traffic flow on a beach. Telecommunication companies use mathematical modeling to determine the charge of the call that consumers make. Scientists also use mathematical modeling to predict the trend in population growth and the spread of infectious disease to ensure the well-being of human race. What will you learn in this chapter? In this chapter, you will be introduced the process of constructing mathematical models, which is called mathematical modeling. In mathematical modeling, a real-world problem will be translated into a mathematical problem. We then solve the mathematical problem and interpret its solution in terms of the real-world problem. Consider the following problem. The population of town A is 40,000. It is known that 45% of the residents in the town practice the habit of recycling used plastic drinking bottles. If each person in the town uses 5 plastic drinking bottles per week, how many bottles are recycled each week in the town? This type of question is often asked in mathematics books to reinforce the concept of percentage. This is an example of a problem-solving question. The problem explicitly gives us all the information we need. We only need to determine the appropriate computation to arrive at one correct answer. This kind of problem-solving question can be used to help us understand a particular mathematical concept and reinforce important mathematical skills. Let's look at the following question. How long does it take to clean up an oil spill in the ocean? The second question is quite different. We do not have enough information to answer this question. It is an open-ended question. We usually do not have complete information when trying to solve real-world problems. The real-world problems demand us to use both mathematical knowledge and creativity to solve them. In this case, mathematical modeling is perfect for solving such open-ended questions. There are 6 important components in mathematical modeling. The first one is identifying and defining the problems, making assumptions and identify the variable, applying mathematics to solve problems, verifying and interpreting solution in the context of the problem, defining the mathematical model. The last one is reporting the findings. There are 6 important components in mathematical modeling. The modeling process can be simplified as shown in the diagram. The first one is real-world problem, then is identifying and defining the problem, making assumptions and identify the variable, applying mathematics to solve problems, verifying and interpreting solution in the concept of the problem, refining the mathematical model, repeat as needed, reporting the finding. Let's look about one mathematical modeling example that involves all the above components. Real-world problem. The grocery store, which is far from your house, sells a pack of 6 kg rice at a lower price than the one closer to your house. Is it worth the drive of the cheaper deal? Identifying and defining the problem. The price of pack of 6 kg rice and the cost of petrol. Determine the distance from the two stores to your house respectively. Find the information needed from the internet. For example, the price of a pack of 10 kg rice from each store, the distance of each store from your house, the current petrol price, the car petrol consumption rate, and so on. Then we must making assumption. The road between the house store A and store B is a perfect straight line. Driving car to the store, purchasing the same number and brand of rice at store A and store B. Then we must identify the variable. Let A as the distance between store A and store B. P1 equal to the price of a pack of 10 kg rice at store A. P2 equal to the price of a pack of 10 kg rice at store B. M equal to the petrol consumption rate of the car in km per liter. N equal to the number of the pack of 10 kg rice to be purchased. H equal to the current petrol price in ringgit per liter. S equal to the difference in price in ringgit of purchasing a pack of 10 kg rice at store B as compared to store A. T equal to the difference in the cost of petrol in ringgit for driving to store B as compared to store A. Applying mathematics to solve problem. We also use in this type of question. The price of a pack of 10 kg rice. Store A is equal to 25 ringgit 95 cent. Store B is 23 ringgit 99 cent. We can let the quantity of 10 kg rice to be purchased be 2 packs. The price to be paid. Store A. 2 times 25 ringgit 95 cent is equal to 51 ringgit 90 cent. Store B. 2 times 23 ringgit 99 cent is equal to 48 ringgit 98 cent. Therefore, by purchasing the rice at store B, one can save 3 ringgit 92 cent. Then, we can let the distance between store A and store B be 6 km. The petrol consumption rate of a car can be approximately 70.6 km per liter. The current petrol price be 2 ringgit and 8 cents per liter. Petrol needed for the 6 km route equal to 0.341 liter. Cost of petrol of the 12 km two-way route is equal to 1 ringgit 42 cents. Therefore, we can save 2 ringgit 50 cents by purchasing 2 packs of 10 kg rice at store B. Next, we can verify interpreting the solution in the context of the problem. The resulting mathematical model is as follows. If x bigger than t, then it is sensible to drive to store B to purchase rice and save more money. If x smaller and equal to t, then we should not drive to store B to purchase rice. Example of using model. X is equal to 25.95 minus 23.99 times 2. So x is equal to 3 ringgit 92 cents. T is equal to 6 divided by 70.6 times 2.08 times 2. So T is equal to 1 ringgit 42 cents. Since x is bigger than t, you should save more money by purchasing rice at store B. Hence, it is sensible to drive to store B. so that the mathematical model is able to solve the problem. Besides, we can find the further explosion too. If all the variables remain the same, how far can store B be located so that it is an optimum choice? P1 minus P2 times n bigger than x divided by m times h times 2. So x is smaller than 16.6 km. This means that if the distance between the two stores is less than 16.6 km, then it is sensible to drive to store B to purchase rice. What is maximum price of a pack of 10 kg rice at store B that will attract a person drive to store B to purchase is P1 minus P2 times n bigger than x divided by m times h times 2. So P2 is more than 25 ringgit 24 cents. This means that if the price of a pack of 10 kg rice at store B is less than 25 ringgit 24 cents, then it is worth the trip. Next, we can refining the mathematical model. The assumption made regarding the route between the house, store A and store B is a straight line need to be revised. If the route between the three places is not a straight line, like a triangle, how does this impact our model? If new assumptions are being made, then the model needs to be revised to reflect this change. Last step is reporting the findings. Use symbol and diagram when necessary to report the finding. The symbol and diagram will depict the whole modeling process until it leads to result. Every model has strength and weakness. What is important is that the model identifies those strengths and weaknesses in the report. For example, the value of a person's time is not considered in the model. Is it worth driving an extra 12 km for someone to save 2 ringgit 50 cents? According to this model, saving 5 cents is considered worthwhile. The model did not account for any environmental consideration. Is it environmentally responsible to drive an extra 12 km just to save 2 ringgit 50 cents? This model does not account for environmental efforts such as an effort to reduce carbon emissions. We have seen the mathematical modeling process work by one example as shown above. Next, we want to discuss about two more questions in mathematical modeling. The journey of a boat moving upstream with cover two places located one on the river bank takes 6 hours. The return journey of the boat moving downstream takes 5 hours. If the speed of river current is 2 km per hour, what is the speed of the boat on calm water? A. Identify and define the problem. B. Determine the assumption that need to be made and identify the variable in solving the problem. In this problem, we know the speed of the river current and the travel time between the two places on the river bank. We need to find the speed of the boat on calm water. B. Assumption that need to be made. Speed of the river current and speed of the boat do not change all the time. The effect of friction between the surface of the boat and the river as well as the wind resistance which can affect the actual speed of the boat are ignored. The variables involved are v of the speed of the boat, t for the travel time, and x for the distance between the two places along the river bank. Then I will explain about question number 2. The diagram below shows the cross-section of a river. A hydrologist measures the depth of the river, y meter, at different distance x meter from the river bank. The results obtained are given in the following table. Distance from the riverbank x meter is 0, 4, 8, 12, 18, 25, 30, while depth of the river y meter is 0, 1.5, 2.3, 2.9, 2.9, 1.7, and 0. We must show how the hydrology used the data above to determine the depth of the river through mathematical modeling. The first step is identify and defining the problem. In the question, we can know about the problem, how to determine the depth of the river. Then, we must make an assumption and identify the variable. We must assume the river is the deepest in the middle with the depth decreasing to 0 at the edges. The two variables involved in this study are the depth of the river y meter and the distance from the riverbank is x meter. The third step is applying mathematics to solve problem. We must write the distance from the riverbank and the depth of the river as a set of order pair x, y. We can get the data from the table and draw a graph for the data. The data seems to rise and fall in a manner similar to a quadratic function. The graph drawn shows the curve of best fit and resemble the graph of a quadratic function. In mathematical modeling to represent the actual situation, the approximate value is used. Based on the graph, the depth of the river is 3 meters, when the distance from the riverbank is 15 meters. Next, we can verifying and interpreting solution in the context of the problem. Based on the graph, we can determine the related quadratic function of the form y equal to ax squared plus bx plus c. We also can determine the constant a, b, and c by substituting any three data. Based on these three data, we can substituting to the equation to find the answer. After substituting, c is equal to 0. 1.7 is equal to 625a plus 25b plus c. 0 is equal to 900a plus 30b plus c. Since c equal to 0, the system of two linear equations in two variables is 1.7 equal to 625a plus 25b is equation A. 0 equal to 900a plus 30b is equation B. From equation B, b is equal to negative 30a. We can substitute c into a. 1.7 equal to 625a plus 35 times negative 30a. The answer is a equal to negative 0.0136. Then we can substitute a equal to negative 0.0136 into equation C. B is equal to negative 30 times negative 0.0136. The answer is 0.408. Hence, the possible quadratic function y is equal to negative 0.0136x squared plus 0.408x. After that, we can substitute x equal to 15, y equal to negative 0.0136 times 15 squared plus 0.408 times 15. The answer is 3.06. We can approximate to the answer obtained from the graph. Then we can refining the mathematical model. For this model, we assume that the river is the deepest in the middle. This may not be true for some other rivers. A new model will be needed if we have new assumptions. The answer will be more accurate if more data have been collected. Last step is reporting the findings. we can write a full report following the above modeling framework structure. In conclusion, we can start the mathematical modeling process in identifying and defining the problem. Then we can making assumption and identify the variables. The third step is applying mathematics to solve problem and verifying and interpreting solution in the context of the problem. Then we can need to refine the mathematical model. We need to identify and define the problem again. If not, we can reporting the finding. That's all for today. Thank you for watching my video.
This is all of my presentation. Thank you for watching.